Graph out-of-distribution generalization is a pressing challenge in graph learning, where models struggle to adapt to unseen graph topologies. To address this, the authors introduce a novel learning strategy that leverages label and environment causal independence, or LECI, to exploit environment information and mitigate graph topology shifts. LECI is rooted in causal subgraph discovery, which is hindered by two key challenges: identifying causal subgraphs and generalizing across environments. The authors propose an adversarial learning strategy to jointly optimize these properties, providing theoretical guarantees for causal subgraph discovery. This approach involves training a graph neural network to predict causal subgraphs, while an adversarial environment generator tries to deceive the network by creating diverse graph topologies. The authors evaluate their method on both synthetic and real-world datasets, demonstrating significant improvements over prior methods. The results establish LECI as a practical and effective solution for graph out-of-distribution generalization. By incorporating environment information and causal independence, LECI enables graph models to generalize more effectively across diverse graph topologies, paving the way for more robust graph learning applications. The section discusses background and related works in graph out-of-distribution, generalization, focusing on environment-based algorithms. It defines an attributed graph as G equals X, A, element of G, where X and A represent the node feature matrix and adjacency matrix, respectively. The paper highlights the importance of identifying causal subgraphs to make predictions robust to distribution shifts, a key goal of many existing graph methods. Environment-based invariant learning algorithms classify data into environments and incorporate environment shift information into neural networks to improve generalization in test environments. The paper emphasizes the accessibility of environment information in graph tasks, particularly in the graph out-of-distribution, benchmark and drug It distinguishes between two stages: environmental inference, predicting environmental labels, and environmental exploitation, using pre-acquired environmental labels. The proposed method, LECI, bypasses the environmental inference phase and introduces a graph-specific environmental exploitation algorithm. The authors of the research paper formalize the problem of out-of-distribution, generalization in graph-structured data, focusing on a causal and data generation perspective. They identified three key topology distribution shift assumptions: covariate shift, fully informative invariant features, FIIF, and partially informative invariant features, PIIF. These assumptions are visually represented in Figure 1 as structural causal models, SCMs, where each node denotes a variable, and each directional edge signifies causation. In the covariate shift assumption, the graph consists of a causal subgraph GC and a spurious subgraph GS. The causal subgraph GC determines the target variable Y, while the spurious subgraph GS is controlled by an exogenous environment E. The core assumption made by the authors is that there exists a component GC within G such that the probability distribution of Y given GC remains invariant across different environments. However, the problem emerges when the distributions of the environment variable E differ between the training and testing datasets, resulting in shifts in the distributions of GS and G. This poses challenges in discovering causal subgraphs for addressing topology distribution shifts. Specifically, two precision challenges are identified: selecting a causal subgraph that may contain spurious structures, and identifying the correct causal subgraph when there are multiple possible subgraphs that satisfy the invariance condition. To address these challenges, the authors propose jointly optimizing label and environment causal independence to effectively learn causal subgraphs. This approach aims to resolve scenarios where the supports of the environment variable E differ between the training and testing datasets. This method is further extended to both FIIF and PIIF assumptions, which introduce additional spurious correlations between GS and Y. The invariant prediction process focuses on selecting the causal subgraph GC using an interpretable subgraph discovery network in the LECI framework. This involves two causal independence properties: E up tag GC, ensuring independence between the environment factor E and the causal subgraph GC, and Y up tag GS, which filters out spurious subgraphs by enforcing independence between Y and GS. The LECI practical solution uses an interpretable subgraph discovery network to learn label and environment causal independence, comprising a subgraph selector and an invariant predictor. The predictor models the distributions of GC given G and Y given GC, respectively. The development of environment adversarial training criterion, EA, and label adversarial training criterion, LA, is crucial for learning causal graphs. To achieve this, the authors introduce a subgraph selector module that utilizes Gumbel sigmoid to bypass non-differentiable sampling processes in the subgraph discovery network. The training loss for this network is defined as the negative log likelihood of the probability of the target variable Y given the complementary graph, denoted as GC. To enforce the causal independence property between the environment E and the complementary graph GC, the authors define the environment adversarial training criterion, which involves minimizing the mutual information between E and GC. This criterion is reformulated in terms of a negative log likelihood form, utilizing an optimal discriminator GE to approximate the probability distribution P, E, GC. Similarly, to enforce the causal independence property between the label Y and the subgraph Gs, the authors introduce a label discriminator GL to model the probability distribution P, Y, Gs. The label adversarial training criterion is then defined as minimizing the mutual information between Y and Gs, also reformulated in a negative log likelihood form. Notably, the optimal parameters for the environment adversarial training criterion and the label adversarial training criterion, denoted as theta asterisk operator E and theta asterisk operator L, respectively, are not unique. Instead, they represent two sets of optimal parameters that satisfy the training criteria. A more detailed discussion on these criteria, along with a relaxed version of LA, is provided in the theoretical analysis section. The authors introduce an adversarial training process to discover a causal subgraph, GC, independent of environment variables E, by optimizing the environment discriminator GE, label discriminator GL, and subgraph selector F theta. This is achieved by minimizing the negative log likelihoods for GE and GL, and adversarially maximizing the losses for F theta. Theoretical guarantees for subgraph discovery are provided under three data generation assumptions outlined in section 3.1. Specifically, Lemma 3.4 states that a subgraph GP of input graph G is a subset of GC if and only if GP is independent of E. Lemma 3.5 formulates the environment adversarial, EA, training criterion, ensuring that the predicted GC is a subset of GC if and only if the model parameter theta is in the optimal set theta asterisk operator E. Additionally, Lemma 3.6 proves that under the covariate SCM assumption, the optimal parameter set theta asterisk operator L satisfies the label independence property. The first subgraph discovery guarantee is presented in Theorem 3.7. Stating that GC equals GC if and only if theta is in the intersection of theta asterisk operator E and theta asterisk operator L. However, Theorem 3.7 does not ensure causal subgraph discovery under FIIF and PIIF SCMs. Therefore, a more robust subgraph discovery guarantee is formulated in Theorem 3.8, stating that GC equals GC if and only if the LA criterion is optimized under the optimal EA training. The authors also address the issue of pure feature shifts, where spurious information may only be present in the node features. To tackle this, they propose a technique to transform the original node features into environment-free node features by removing the environment information, thereby addressing distribution shifts on node features X. The authors introduce their proposed method, LECI, designed to address graph out-of-distribution, OOD, problems. LECI consists of three main components: causal subgraph selection, environment exploitation regularization, and feature filtering. The computational complexity of LECI is O(MD plus ND2), comparable to message-passing neural networks. Extensive experiments compare LECI with various baselines on synthetic and real-world datasets, showing consistent outperformance and results close to the oracle on the good motif dataset. The authors also investigate OOD performance under different assumptions using the CFP motif dataset, demonstrating stability across hyperparameter settings. Each component of LECI is crucial for optimal performance. The results of various out-of-distribution (OUD) methods on structure and feature shift datasets are presented in Table 1. These results showcase classification accuracies on test sets with standard deviations in parentheses, obtained through an automatic hyperparameter selection process with 3 runs. LECI significantly outperforms all baselines by a large margin on the feature shift problem, indicating a substantial improvement of the method. A feature shift sanity check is performed on GOODCMNIST, where each graph consists of a colored handwritten digit transformed from MNIST via superpixel technique. The environment labels control the digit colors, and the challenge is to generalize to unknown colors in the test set. Figure 3 provides an interpretability visualization of LECI, displaying the results with 3 motifs, crane, house, cycle, on both the training set with 3 base graphs, ladder, tree, wheel, and the OUD test set with Dorigo-Tseb-Mendez graphs as their basis. The motifs and base graphs are colored as green and orange nodes, respectively, and the selected causal graphs are denoted by red edges. The authors observe that although subgraph discovery methods are possible to address size shifts, they are more sensitive than general GNNs. The OUD test set hyperparameter selection is applied to compare the theoretical potentials of different OUD principles in Appendix F.1. Furthermore, the authors investigate the ability of different learning strategies to generalize to graphs with different unknown base subgraphs. LECI's ability to select motifs accurately indicates that it eliminates most spurious subgraphs to make predictions, which is the key reason behind its ability to generalize to graphs with different unknown base subgraphs. The paper then proceeds to practical comparisons, aiming to answer research questions RQ2, RQ3, and RQ4 by conducting experiments on real-world scenarios, including molecular property prediction tasks on various datasets such as GOODHIV and drug OUD LBAPCOREIC50. The authors present the performance of 10 methods on real-world datasets, including GOODSST2, Good Twitter, GoodHiv Scaffold, GoodHiv Size, and drug OUDassay. The results are reported in terms of accuracy for the first 2 datasets and ROCAUC for the latter 2. LECI achieves the best results over all baselines on real-world datasets, demonstrating consistent and effective performance regardless of whether the validation set is from the in-distribution or out-of-distribution domain. A hyperparameter sensitivity study is conducted, examining the effect of hyperparameters lambda E and lambda L on the performance of LECI on the Good Motif and Good Twitter datasets. The results show that LECI demonstrates robustness across different hyperparameter settings and consistently outperforms ERM. The authors also study the training stability and dynamics of LECI, plotting the OUD test accuracy curves for LECI and the baselines on Good Motif and GOODSST2 during the training processes. The results indicate that LECI has a stable training process with desired training dynamics, converging to top-grade performance without further degradation. This suggests that LECI is practical to implement in real-world scenarios. Overall, the results demonstrate the effectiveness and stability of LECI in real-world scenarios, making it a promising method for out-of-distribution generalization. The stability study of the proposed LECI model is examined through its performance during training on Good Motif and GOODSST2 datasets. The OUD test accuracy curves illustrate the point at which independence constraints take effect. Initially, the training process fosters a conducive environment for discriminator training, essential for generalization optimization. An ablation study demonstrates the effectiveness of LECI components, including environment adversarial training, label adversarial training, and pure feature shift consideration. The results show that partial independence leads to suboptimal performance, whereas combining environment and label adversarial training significantly improves performance in structure shift datasets. This highlights the importance of addressing subgraph discovery challenges. Experiments demonstrate LECI's practicality and effectiveness in handling out-of-distribution generalization in graph data, outperforming existing baselines on both synthetic and real-world datasets, and displaying robustness to hyperparameter settings. LECI's interpretable architecture and training stability make it a promising solution for real-world applications. The incorporation of two causal independence properties is proposed to enhance causal subgraph discovery in graph-OOD generalization. Unlike previous graph-OOD works, LECI leverages environment labels, widely used in computer vision and accessible in graph learning areas. The significance of environment labels is empirically validated through experiments and supported by recent works like G-Splice and GALA. This research paves the way for future graph environment-centered methods. This research was made possible by funding from the National Science Foundation. The study focuses on developing a novel machine learning framework for predicting materials' properties, specifically the glass transition temperature of polymers. This is achieved through a combination of molecular dynamics simulations and graph neural networks. The authors employ a dataset of 1,000 polymer structures, generated using a Monte Carlo algorithm, to train their model. The proposed framework consists of two primary components: a graph neural network encoder and a feed-forward neural network predictor. The encoder extracts molecular features from the input polymer structures, while the predictor outputs the predicted glass transition temperature. The authors utilize a mean-squared error loss function and an atom optimizer to train the model. The results show that the proposed framework outperforms existing methods, achieving a mean absolute error of 10.2 K. The authors attribute this improvement to the ability of graph neural networks to capture complex molecular interactions. Furthermore, they demonstrate the scalability of their approach by applying it to a larger dataset of 5,000 polymer structures. The study highlights the potential of machine learning in accelerating materials discovery and design. However, the authors acknowledge the limitations of their approach, including the reliance on high-quality training data and the need for further validation. Future work includes exploring the application of this framework to other materials' properties and integrating it with experimental techniques. Causal inference is a crucial aspect of machine learning, particularly when it comes to out-of-distribution generalization. Understanding the data-generating process is essential for making accurate predictions and generalizations. Seminal works on causality, 17, 18, provide a foundation for understanding the relationships between variables in a system. Methods for achieving out-of-distribution generalization include environment augmentation, 20, invariant prediction, 21, and graph structure and feature extrapolation, 19. However, invariant risk minimization, 24, poses challenges, as it risks overfitting to the training environment. Generative models, such as GANs, 33, can create synthetic data to augment the training set and improve generalization capabilities. Hierarchical graph representations can be learned using techniques like adaptive structure-aware pooling, 34. Correlation alignment for deep domain adaptation, 35, aims to align the second-order statistics of source and target domains, improving performance on unseen data distributions. The evolution of networks, 36, highlights the importance of understanding the underlying structure of complex systems for making accurate predictions and generalizations. Understanding causal relationships and the data-generating process is crucial for achieving robust out-of-distribution generalization in machine learning models. This understanding allows models to generalize well to new, unseen data distributions, which is critical in many real-world applications. The page delves into various research papers on geometric deep learning on graphs and manifolds, focusing on explainability in graph neural networks, out-of-distribution generalization, and distribution-ally robust optimization. It also covers stable learning via sample reweighting, heterogeneous risk minimization, and a survey on transfer learning. Furthermore, the content includes discussions on deep visual domain adaptation, understanding feature learning in out-of-distribution generalization, and a unifying view on dataset shift and classification. This section of the research paper provides a comprehensive overview of various methodologies and techniques employed in unsupervised domain adaptation, source-free domain adaptation, and domain generalization. It begins by discussing the contrastive adaptation network proposed by Kong et al., which aims to align the feature distributions across different domains without labeled target data. The authors also mention the work of Gannon and Lempitsky, who introduced the concept of unsupervised domain adaptation through backpropagation. The paper further highlights the contributions made by Tsai et al., who proposed a structured output space adaptation method for semantic segmentation tasks. The research paper discusses various studies and techniques related to graph neural networks, GNNs, and their applications in different domains. It begins by citing a study on Pareto invariant risk minimization, which aims to mitigate the optimization dilemma in out-of-distribution generalization. The paper also explores techniques for improving GNN's robustness against adversarial attacks, highlighting the importance of graph attention mechanisms in enhancing model performance. Additionally, it delves into the application of GNNs in social network analysis, emphasizing their potential in understanding and predicting complex social dynamics. Graph neural networks, GNNs, have been a significant focus in recent research, particularly with regards to their attention mechanisms, size generalization, and explainability methods. A key paper by Boris Nyazev et al., Understanding Attention and Generalization in Graph Neural Networks, delves into the intricacies of GNN's performance. This work highlights the importance of understanding how attention mechanisms contribute to GNN's ability to generalize across different graph sizes. Another notable contribution comes from Beatrice Bevilacqua et al.'s paper, Size-Invariant Graph Representations for Graph Classification Extrapolations. This research emphasizes the need for size-invariant graph representations to enhance GNN's capacity for generalization. Explainability methods are also crucial in making GNNs more transparent. Papers such as Gene Explainer by Jitao Yang et al. And Explainability Methods for Graph Convolutional Neural Networks by Philip E. Pope et al. Explore various techniques to demystify GNN's decision-making processes. These studies demonstrate the potential of explainability methods in enhancing trust and understanding in GNNs. In summary, the discussed papers collectively contribute to advancing our understanding and improvement of GNNs. They emphasize the importance of attention mechanisms, size generalization, and explainability methods for enhancing GNN's performance and transparency. Graph neural networks have emerged as a powerful tool in machine learning, with various research papers exploring their applications and advancements. The information bottleneck method, a fundamental concept in deep learning, has been instrumental in shaping the development of graph neural networks. This method, which involves maximizing the mutual information between the input and output while minimizing the mutual information between the input and the bottleneck layer, has been crucial in learning representations of graph-structured data. Graph-UNets, a type of graph neural network, have been widely used in machine learning tasks, including node classification, graph classification, and edge prediction. Variants of graph-UNets, such as graph attention UNets and graph residual UNets, have also been proposed to improve performance in specific tasks. The significance of graph neural networks lies in their ability to perform semi-supervised classification, where they can learn from limited labeled data and generalize well to unseen data. Recent advancements in graph pooling networks have further enhanced the capabilities of graph neural networks. Graph pooling networks, which aim to downsample the graph while preserving its essential information, have been shown to improve the performance of graph neural networks in various applications. Additionally, principal neighborhood aggregation for graph nets has been proposed as a method to aggregate features from neighboring nodes, leading to better node representations. The evolution and diversity of research in graph neural networks are evident in the various papers discussed, which collectively demonstrate the power and potential of graph neural networks in machine learning tasks. The LECI paper's appendix delves into the broader impacts of the research, highlighting its significance in environmental and fairness contexts. It also provides a detailed discussion on related works, including extensive background discussions on environment-based graph-OOD methods. Theoretical discussions encompass proofs, comparisons with previous graph-OOD methods, and discussions on precision challenges and limitations. The appendix also details the implementation of the LECI model, including the architecture of the subgraph selector and the pure feature shift consideration. Experiment settings are outlined, featuring fairness discussions, datasets used, baseline selection, training settings, and hyperparameter sweeping. Supplementary experiment results are presented, focusing on the ability to address structure and feature shifts, as well as interpretability visualization results. This comprehensive approach underscores the depth and breadth of the research, emphasizing its potential to significantly impact environmental and fairness contexts. The page discusses the challenges of out-of-distribution generalization in graph learning, particularly in real-world deployment scenarios where data collection is limited to certain domains. It highlights the importance of integrating underlying physical mechanisms into graph neural networks, GNNs, through a causality lens. The section provides an extensive background on generalization, including its relation to transfer learning, domain adaptation, domain generalization, causality, and invariant learning. It emphasizes the significance of understanding and addressing the distribution shift, especially in scenarios where data privacy concerns or the necessity to retrain after collecting target samples is impractical. The concept of invariant learning is revisited as an optimization process, building upon popular data generation assumptions such as PIIF, FIIF, and anti-causal assumptions. These assumptions have been widely adopted in various works, providing theoretical support for domain generalization, DG, and aligning with the DG setting. The definition of dataset shifts is re-examined, and the covariate data generation assumption is illustrated in Figure 1, which is a common assumption in DG. Graph out-of-distribution generalization has garnered significant attention, with applications in non-Euclidean data. Graph neural networks, GNNs, have been shown to possess superior generalization capabilities. Prior works have explored graph generalization in terms of graph sizes, and recently, causality modeling-based methods have been proposed for both graph-level and node-level tasks. However, these methods have limitations, including incomplete data assumptions and the need for environment exploitation methods for evaluation. Environment inference methods, such as EERM, MRL, and GIL, have gained traction in graph tasks, but they face challenges, including the need for environment exploitation methods and the injection of human assumptions to generate environment partitions. This paper aims to aid in building better graph-specific environment exploitation methods for evaluating environment inference methods. Graph augmentation is also a promising approach to boost model generalizability, with recent works exploring environment-directed extrapolating graphs in both feature and non-Euclidean spaces. The relationship between GNN explainability, interpretability, and graph generalization is discussed, highlighting the importance of subgraph-based graph data generation (SCMs). The paper is compared to previous graph works, including DIR and GSAT, which propose new subgraph selection architectures. In contrast, this paper proposes a learning strategy that can apply to any subgraph selection architectures, providing both sufficiency and necessity guarantees to solve the two subgraph discovery challenges under three data generation assumptions. In the realm of machine learning, deep neural networks, DNNs, have emerged as a powerful tool for modeling complex patterns in data. However, their black box nature and lack of interpretability hinder their widespread adoption in high-stakes applications. To address this, researchers have proposed various techniques for explaining DNN decisions, including saliency maps, feature importance, and model interpretability methods. One such approach is the use of attention mechanisms, which allow the model to focus on specific input features or regions when making predictions. Attention-based models have been successfully applied to various natural language processing (NLP) tasks, including machine translation, question answering, and text classification. Recently, researchers have introduced the notion of explainable attention, which aims to provide insights into the decision-making process of attention-based models. This is achieved by generating attention weights that are not only predictive but also interpretable. The proposed approach, dubbed attentive explanation, leverages the concept of attention to generate explanations for DNN decisions. The AE framework consists of two main components: attention-based feature importance and attention-based explanation generation. The former involves computing attention weights for each input feature, which are then used to generate feature importance scores. The latter involves generating explanations for the predicted output by analyzing the attention weights and identifying the most relevant input features. Experimental results on several benchmark NLP datasets demonstrate the effectiveness of AE in generating accurate and interpretable explanations for DNN decisions. Furthermore, the proposed approach is shown to outperform existing explanation methods in terms of explanation quality and faithfulness to the original model. Limitations of the study include the reliance on attention mechanisms, which may not always provide accurate explanations, and the need for further evaluation on more diverse datasets. Future work involves exploring alternative explanation methods and integrating A with other model interpretability techniques to provide a more comprehensive understanding of DNN decisions. Recent environment inference methods at the graph and node levels are limited by their failure to incorporate graph-specific environment exploitation techniques. In contrast, the proposed method, LECI, exploits the graph structure for environment inference. A comparison of LECI with previous environment-based graph out-of-distribution methods, MRL, GIL, and EERM, highlights its unique incorporation of graph-specific environment exploitation, Table 4. Graph-specific environment exploitation is defined as the direct application of the environment partition assistant to graph-specific components, such as the adjacency matrix, rather than common hidden representations. A replacement test is proposed to assess graph specificity, where the environment exploitation optimization remains valid after replacing the graph neural network, GNN, with feature vectors and a multi-layer perceptron, MLP. The optimization objectives of MRL, GIL, and EERM are analyzed, revealing that these methods are not graph-specific. Equations 9a, 9b, and 9c demonstrate that these methods can be reformulated using feature vectors and MLPs, indicating a lack of graph-specific component leverage. In contrast, LECI's environment optimization is inherently graph-specific and cannot be reformulated using feature vectors and MLPs, relying on graph-specific operations such as subgraph discovery and adjacency matrix manipulation. To ensure a fair comparison, LECI is compared with the environment-based GraphOOD baseline, GIL, by replacing GIL's subgraph discovery architecture with GSAT under the same network structure. This comparison highlights the advantages of LECI's graph-specific environment exploitation approach. The environment exploitation phase is conducted using the official IGA implementation from DomainBed, with hyperparameter sweeping space aligned with the original GIL paper. The out-of-distribution, OOD, validated test results are presented in Tables 5 and 6, comparing the performance of GIL and LECI on various datasets, including motif base, motif size, CMNIST, GOODSST2, good Twitter, goodHIV scaffold, goodHIV size, and drug assay. The results show that, except on Twitter, GIL produces suboptimal results compared to LECI. Theoretical proofs of the relaxed independence property are provided, including proposition C1, which states that for any graph GP and its subgraph GS, the mutual information I, GS, Y, is less than or equal to I, GP, Y. The proof demonstrates that the conditional entropy H, Y, GS, is greater than or equal to H, Y, GP, by considering a random graph GS consisting of a set of random variables, edges, is, and showing that H, Y, GS, equals H, Y, as, is greater than or equal to H, Y, AS. A plus, equals H, Y, AP, equals H, Y, GP. Additionally, the proof of proposition 3.3 is provided, which involves finding the optimal discriminator phi E that minimizes the Kullback-Leibler divergence between P, E, GC, and P phi E, E, GC. The proof shows that the optimal discriminator phi asterisk operator E is the one that minimizes the mutual information I, E, GC, minus the entropy H, E, which is equivalent to argmin phi E KLHP, E, GC, parallel P phi E, E, GC, I. This section delves into the intricate analysis of lemmas and theorems that underpin the proposed graph learning strategy. It commences with the proof of lemma 3.4, which posits that a subgraph GP is a subset of the causal graph GC if and only if GP is independent of the environment E. This proof leverages mutual information and the contradiction principle. Subsequently, the paper presents the proof of lemma 3.5, which establishes a relationship between the predicted causal graph GC and the optimal parameter theta. It demonstrates that GC is a subset of GC if and only if theta belongs to the set of optimal parameters for the environment adjustment, EA, training criterion. The paper then proceeds to prove theorem 3.7, which integrates the results from the previous lemmas to conclude that under certain assumptions, the predicted causal graph GC equals the true causal graph GC if and only if both the EA and local adjustment LA training criteria are optimized. This theorem underscores the importance of considering both types of adjustments in the learning process. Furthermore, the paper provides the proof of Theorem 3.8, which shows that under specific conditions, the true causal graph GC equals the predicted causal graph GC when the LA criterion is optimized under the optimal EA training. This result reinforces the significance of the interplay between EA and LA training criteria in achieving accurate graph learning. Finally, the section compares the proposed method with other recent graph-OOD learning strategies, emphasizing the distinctiveness of the data generation assumptions, motivated challenges, and invariant learning strategy employed in this work. The comparison is summarized in Table 7, providing a comprehensive overview of the key differences and advantages of the proposed approach. In the realm of out-of-distribution generalization in graph data, two primary challenges persist: precision challenges. To address these challenges, this study proposes the LECI method, which is compared to prior methods, including DIR, GSAT, SIGIV1, and SIGIV2, in Table 7. The comparison highlights LECI's unique capability to tackle both precision challenges under three data generation assumptions: FIIF, PIIF, and the relaxed property. In contrast, prior methods either fail to address these challenges or rely on impractical assumptions. For instance, DIR and GSAT are incapable of addressing precision challenges, whereas SIGIV1 and SIGIV2 have limitations due to their requirements for true subgraph size information or independent components assumptions. LECI's innovative approach, which exploits environment information and learns causal independence, makes it a promising method for OOD generalization in graph data. Table 8 provides a comprehensive comparison of the assumptions underlying each method, including data generation assumptions, theory, and theoretical guarantees. This comparison reveals that LECI's use of simple, annotated, grouped environment partitions is sufficient to outperform many sophisticated human-designed assumptions. The importance of addressing the two precision challenges simultaneously to achieve invariant graph neural networks is emphasized. Moreover, explicit comparison and analysis of assumptions are essential, as many previous works rely on unilateral causal analysis without discussing and comparing assumptions explicitly. The section discusses the challenges in solving two subgraph discovery challenges, focusing on the difficulties in maximizing mutual information between the selected subgraph and the label. Even with an invariant predictor, gradients can be hindered by undefined continual states, leading to insufficient support for maximizing I, Y, GC. The subgraph selector maintains invariance under distribution shifts through assumptions like the causal subgraph equal support assumption, CSES, architecture, and information sufficiency. It operates as a classifier, classifying hop egographs into either label 1, part of GC, or label 0, not part of GC. The distribution of F theta is only affected by the support of P, GK_C, ensuring GC with unseen GS can still be recognized. The paper relaxes the CSES assumption and introduces the concept of locality rate to loosen the global equal support requirement to a local one. It also presents a proposition stating there is no hop subgraph that shares across P, GC, and private GS, with a proof by contradiction. This section concludes with an analysis of the challenges and limitations in subgraph discovery, emphasizing the interplay between the subgraph selector and the invariant predictor. The proposed method, as depicted in Figure 6, is designed to enforce independence properties within a graph causal model by employing a subgraph selector F theta. This architecture is crucial for maintaining the invariance of P, GC, G, under the specified data generation assumptions. However, challenges and limitations arise due to the utilization of common adversarial training, which necessitates longer training times and optimal discriminator attainment. Furthermore, the subgraph discovery architecture used can complicate the training process, requiring additional information from both subgraph branches for comprehensive optimizations. Future research directions could involve developing new subgraph discovery architectures that alleviate these challenges. The method may not directly correlate with out-of-distribution (OOD) errors, although it offers practical solutions capable of addressing a wider range of shifts. Bridging this method to OOD generalization errors presents a substantial challenge. Future studies could consider a wider range of data generation assumptions, exploring edge-level, node-level, or even flow-level considerations to contribute to the continuous evolution and refinement of graph OOD models. The pure feature shift consideration (PFSC) architecture is illustrated in Figure 7, showcasing the overall network structure. This network employs a small multi-layer perceptron (MLP) transformer, denoted as MLPT, with learnable parameters phi-t to transform node features X into environment-free node features X. This transformation is achieved through an adversarial training process, where the MLP is trained to remove environment information from X, and the feature environment discriminator approximates the correlation between X and the environment E. The objective of this process is formulated as equation 12. The training strategy of LECI involves two primary implementations. The first approach adheres to a rigorous training process, where updates to the subgraph selector are performed only upon the convergence of the two discriminators. This iterative training procedure involving the subgraph selector and the two discriminators continues throughout the training process. However, this approach can be time-consuming. To overcome this limitation, the second implementation optimizes the entire network, including the subgraph selector and the discriminators. Initially, the adversarial training hyperparameters, lambda L and lambda E, are set to 0, restricting the influence of the gradients from the discriminators on the subgraph selector. This ensures a relatively stable distribution of GC and consistent training of the discriminators. As training proceeds and network parameters stabilize over time, with the discriminators moving closer to convergence, the adversarial training hyperparameters are progressively increased. This strategy enables a gradual implementation of the independence constraints, ensuring the discriminators remain near their optimal states without being abruptly disrupted, as depicted in Figure 5. This section of the research paper details the experimental settings, including discussions on fairness, datasets, baseline selection justification, training and optimization settings, hyperparameter settings, and software and hardware environments. The fairness discussion highlights that all reported results are obtained from 3 runs and are selected by automatic hyperparameter sweeping with respect to in-distribution, ID, and out-of-distribution, OOD, validation results. A detailed fairness discussion about the usage of environment information is included in Appendix B.2. 7 datasets are utilized for the experiments, including SST2, motif, and CMNIST from the GOOD benchmark, LBAPCOREIC 50 assay split from DrugOOD, and 3 newly created datasets: GOOD Twitter, CFP motif, and GOODHIV. All dataset splits target domain generalization and align with the guidelines provided in the original literature, except for CFP motif, which incorporates partial indistribution (PIIF) and full indistribution (FIIF) shifts as described in section 4.2. GOODHIV is a compact, real-world molecular dataset derived from MoleculeNet, containing molecular graphs with atoms as nodes and chemical bonds as edges, and the task is to predict a molecule's potential to inhibit HIV replication. GOODSST2 is a sentiment analysis dataset based on real-world natural language, adapted from Yuan et al., where each sentence is converted into a grammar tree graph with nodes representing words and node features derived from word embeddings. GOOD Twitter is a real-world natural language sentiment analysis dataset, adapted from Yuan et al., with a similar transformation process as in SST2. GOODCMNIST is a semi-synthetic dataset designed to test node feature shifts, consisting of graphs built from handwritten digits extracted from the MNIST database. GOOD Motif is a synthetic dataset inspired by spurious motif, created for structure shift studies, where each graph is generated by connecting a base graph and a motif, with the motif solely determining the label. CFP motif is a synthetic dataset similar to GOOD Motif, designed for further structure shift study, with differences in the base subgraphs of the OOD validation and test set, and extensions to FIIF and PIIF shifts. The research paper presents a comprehensive analysis of various datasets and baseline models used in the study. The datasets selected include good datasets and synthetic datasets, which cover a range of molecular predictions and natural language processing tasks. Detailed statistics for these datasets are provided in Table 9. The authors justify their choice of baseline models, including IRM, Virex, Coral, and DAN, which are typical out-of-distribution (OOD) baselines that perform similarly on graph tasks. They omit comparisons with group DRO, EIIL, IBIRM, and CNC, as these models have been shown to be less effective than state-of-the-art graph-specific OOD methods. The paper focuses on graph-specific baselines, highlighting learning strategies within the subgraph discovery architecture. ASAP is presented as a subgraph discovery baseline, while DIR and GSAT are original graph-specific methods for invariant learning. SIGA is discussed as a recent state-of-the-art method that provides a thorough theoretical discussion about graph OOD generalization. DIR and GSAT perform similarly, with SIGA outperforming both IRM and ASAP in real-world scenarios but facing performance shortcomings in synthetic datasets. Other recent graph-specific baselines, such as DISC, MRL, and GIL, are mentioned but not included in the baseline due to specific reasons. DISC is not universally applicable and focuses on different data generation assumptions, while MRL is specific to molecule predictions. Comparing the environment exploration phase with the environment exploitation phase is inherently limited due to the constraints of subgraph discovery architectures. A controlled comparison is essential to overcome these limitations. To achieve this, graph neural networks, GNNs, are employed, specifically the graph isomorphism network, GIN, with tailored parameters for each dataset. The incorporation of virtual nodes is crucial for capturing size shifts, which is a critical aspect of graph-based learning. The training phase utilizes the Atom optimizer, with adaptive learning rates and weight decay rates carefully selected for each dataset. This optimization strategy enables the model to converge effectively and generalize well to unseen data. The hyperparameter sweeping spaces for various methods are presented, including traditional out-of-distribution, OOD, detection techniques as well as more advanced approaches such as ASAP, DIR, and SIGA. These sweeping spaces provide a comprehensive understanding of the optimization landscape, facilitating the identification of optimal hyperparameters for each method. Machine learning models were evaluated on structure and feature shift datasets, with a focus on the performance of local ensemble coding and incremental learning, LECI. The results underscore the importance of hyperparameter selection and validation, particularly for LECI, which requires a specific range to function effectively. Inadequate hyperparameter tuning can lead to invalid training scenarios, characterized by poor model performance and instability. To avoid these scenarios, the golden rule for setting the hyperparameter searching space is to prioritize a robust and efficient search strategy. This involves defining a reasonable range for each hyperparameter, ensuring that the search space is neither too narrow nor too broad. The implementation and deployment of LECI were carried out using a software architecture built on top of Python, scikit-learn, and TensorFlow, running on a hardware architecture comprising NVIDIA V100 GPUs and Intel Xeon processors. This setup enabled efficient processing and scaling of the models. The results of the experiments demonstrate the effectiveness of LECI in adapting to structure and feature shifts, outperforming other machine learning models in certain scenarios. However, the study also highlights the need for careful hyperparameter tuning and validation to unlock the full potential of LECI. Future work involves exploring alternative search strategies and expanding the range of datasets to further validate the performance of LECI. The performance of various methods in identifying causal subgraphs is discussed, with a focus on the leakage of out-of-distribution, OOD, test information. Significant improvements in performance are observed among several methods, but LECI consistently outperforms all baselines. Interpretability visualization results, as depicted in Fig. 8, demonstrate LECI's accuracy in selecting most motifs. This is achieved by applying different base subgraphs and motifs, showcasing LECI's capability in distinguishing and eliminating spurious parts, such as those found in ladders and paths. This highlights LECI's superior ability to accurately identify and interpret causal relationships within complex systems. Figure 8 presents interpretability results on good motif and CFP motif covariate shifts, showcasing the effectiveness of the proposed method in identifying meaningful subgraphs and motifs. The visualization highlights base subgraphs and motifs as orange and green nodes, respectively, while selected subgraphs are denoted by red edges. This enables the identification of the most informative subgraphs and motifs that contribute to the model's predictions, providing insights into the underlying relationships between input features and output variables. The good motif dataset, characterized by a covariate shift in the motif distribution, demonstrates the model's ability to adapt to changes in the data distribution. The CFP motif dataset, featuring a covariate shift in the graph structure, further illustrates the model's robustness in the presence of varying graph topologies. The interpretability results on both datasets underscore the model's capacity to capture complex relationships between motifs and subgraphs, facilitating a deeper understanding of the underlying mechanisms. In high-stakes applications, such as bioinformatics and computer vision, model transparency is essential for building trust and identifying potential biases. By visualizing the selected subgraphs and motifs, the model's decision-making process is demystified, allowing practitioners to refine their models and make more informed decisions. These results build upon the previously introduced graph neural network architecture and motif-based explanation framework, providing empirical evidence for the effectiveness of the proposed method in capturing meaningful relationships between motifs and subgraphs. Future work may involve exploring the application of this method to more complex graph-structured data and investigating its potential in identifying novel biological or chemical insights.